When you are collaborating with people and they all have a similar goal and you have all of this energy, it's not that
And so I cry sometimes when I'm lying in bed just to get it out what's in my head. And I feel it, a little peculiar. And so I wake in the morning and I step outside and I take a deep breath and get real high. And I see to the top of my lungs what's going on. Tries. Oh my God, do I try? I try all the time in this institution.
Vi sitter här i väntan och spelar lite Dota.
I hear you, man.
Vi sitter här i väntan och spelar lite Dota.
I feel you, man.
Vi sitter här i väntan och spelar lite Dota och pushar på och smeker med motståndet vi leker. Vi sitter här i väntan och spelar lite Dota och springer runt och creepar och motståndet vi slipar.
Let's get it on.
Vi sitter här i väntan och spelar lite Dota och pushar på och smeker med motståndet vi leker. Vi sitter här i väntan och spelar lite Dota och springer runt och creepar och motståndet vi slipar. Vi sitter här i väntan och spelar lite Dota och pushar på och smeker med motståndet vi leker. Vi sitter här i väntan och spelar lite Dota och springer runt och creepar och motståndet vi slipar. här i vänten och spelar lite Dota.
I hear you, man.
Vi sitter här i vänten och spelar lite Dota.
I feel you, man.
Vi sitter här i vänten och spelar lite Dota och pushar på och smeker med motståndet vi leker. Vi sitter här i vänten och spelar lite Dota och springer runt och creepar och motståndet vi slipar.
Let's get it on.
Vi sitter här i vänten och spelar lite Dota och pushar på och smeker med motståndet vi leker. Vi sitter här i vänten och spelar lite Dota och springer runt och creepar och motståndet vi slipar. Vi sitter här i vänten och spelar lite Dota och pushar på och smeker med motståndet vi leker. Vi sitter här i vänten och spelar lite Dota och springer runt och creepar och motståndet vi slipar.
Good afternoon, everyone. I think we are ready to start. For this, I'll do recording. Can you hear my voice?
Yes, doctor.
Please. Okay, thank you. Okay, we are going to finish up the last few pages of the slide for FM. Then we are going to move on to chapter 4 for pulse modulation. Before we start, in the WhatsApp group, I already shared the scope for our test, which released today. So you can see for FM, we do not have a circuit. That's mean for frequency modulation. The key part will be on the equation and also calculating of all the parameters, but not circuit. So FM modulator and also FMD modulator is not within the scope of the assessment for test 2. But it will be in the scope for final exam. So that is FM. Then for pulse modulation, we're going to start, I think, shortly today. Pulse modulation is not the whole chapter, is not including non-uniform coding and also not including line coding. So only half of the chapter is within the scope for our test. Okay, let's quickly go into our last part of FM modulation. So on your screen now, what you see now, this is radio FM broadcasting. Radio here means the radio station that we are listening to from our broadcasting station. So radio. Most of the modern radio now use FM. So FM we studied about that in this chapter already. Then usually FM we use for radio broadcasting. That's mean transmitting DJ or also song or news through voice. The frequency being used, where we stopped yesterday, you can see this is example of a receiver for a radio. That's mean a receiver for a broadcasting radio. So things to note here is this is the typical frequency 88 to 108 megahertz. Total 20 megahertz bandwidth being used for different channels or different radio stations. So not one single station only, but this one, that's mean many stations can operate within this range. And this is a range that agreed internationally. So doesn't matter wherever you go, FM radio will be using this frequency range. Okay, so we want to, what we are going to discuss now is from 88 megahertz up to 108 megahertz. This is the 20 megahertz of bandwidth or 200 megahertz of spectrum allocated for radio FM broadcasting. So we want to divide these 20 megahertz into different what you call channel, different channel band, different channel or different band, or in layman sense, different station. For example, channel 1 is for one station. For example, this is music station, and this is belonging to another news station. This is another DJ stations. So that's mean station. That's mean when we choose in our modern communication radio, when we choose, let's say, for example, we tune to 95.4 megahertz, FM 95.4. Usually we say FM 95.4. So this is meaning the channel is using 95.4 megahertz. This is the center frequency. So the center frequency is the middle here. Okay, the center frequency is the middle here. And then the total bandwidth allocated for that particular channel, this particular frequency, is within this scope. How large is this? Total bandwidth is 200 kilohertz. Okay, I repeat again. Look carefully on the screen now. Let's zoom in. For FM broadcasting, FM radio broadcasting, the bandwidth available is from 88 to 108 megahertz. And within 88 to 100 megahertz, you can fit in total 100 channel or 100 radio station. Meaning, if you have 2 megahertz, that means 20,000 kilohertz. This is 2 megahertz. 2 megahertz equal to 2,000 kilohertz divided by 100. What do you call? Divided by 100. No, 20,000. What by 20 by 100 station? That means each station will have 200 kilohertz. Okay, each station will use 200 kilohertz. Okay, they use 200 kilohertz. Then these 200 kilohertz, we focus in this slot only. These 200 kilohertz, this is center frequency. Meaning, typical if you are being asked this question, then you are going to ask you to design. Then you need to understand. So this is the frequency here is 88 megahertz. Because we are using it for 200 kilohertz, that means what's the frequency here? The frequency here will be 88.2 megahertz. That means this one minus this one will become 200 kilohertz or 0.2 megahertz. Okay, so this is equivalent to 0.2 megahertz. So let's look further. So what is the frequency here? The frequency here will be 88.4 megahertz. Okay. Then the center frequency for this particular channel, the center frequency or the way called the carrier. Okay, that's why you see here, the carrier is the needle between this one and this one, which is 88.1 megahertz. So this is the carrier frequency for this particular radio station or radio channel. And for each channel, data only will be transmitted within this 150 kilohertz band. Okay, will be only transmitted within this 100 kilohertz frequency band. 100 kilohertz frequency band. Then on this side here, this side and also this side, upper side and lower side, we'll reserve some empty space. So this is like our house. We build a house where we can occupy, but then at the left side and the right side of the house, we will leave some room. Okay, this room, there's many reasons. Main reason is not to interfere with our neighbors. So that's mean if your signal go up to here, that's mean if you do not have this reserve guard band, your signal might leak to your neighbor channel. So you have a guard band here. So this total guard band will help us to protect. So that's mean the signal in channel 1 will not go to channel 2. So we will avoid the guard band. The purpose of guard band, the purpose of this guard band, 25 kilohertz guard band, is to avoid interference. Interference, that means it's like you are living in one room and this is your neighbor. So this is the wall between them. So if without this wall is very thin, then you will hear whatever your neighbor is talking. Then that will disturb your daily life. So this is the key numbers that you need to understand. Typically, if you be asked question, all this information will be given in written sentences. So you need to read carefully. Another parameter we see here is your frequency deviation. Okay, your frequency deviation. For frequency deviation, you can see delta F equal to plus minus 75 kilohertz. What is delta F? Please take note on your screen now. You remember for FM, what is our beta? The full formula for beta. Quickly, what is the full formula for our FM? So if you go back to very early FM beta. Okay, you can see this is the definition for beta equal to beta omega m. The relationship is given here. So from, if you know the beta, then we can calculate the bandwidth. That means the bandwidth required here. So you can see for signal, FM signal, the bandwidth, the equation is 2n FM. Okay, 2n FM. So if I go back to the slide just now, so this is bandwidth. Bandwidth for wide band FM equal to 2n FM. Bandwidth for narrow band FM, which is very similar to DSB AM, DSB with carrier, full carrier. So the bandwidth is 2 FM. Another simplified method. So this typically for this one, that means beta low. Beta is very low. Later, there's another shortcut. If we do not have this information for us to calculate the bandwidth, there's another shortcut formula we call bandwidth for large beta. Beta equal to large or beta more than 10. Beta more than 10. That means this is beta high value, usually beta more than 10. Then the formula equal to 2 multiply of delta F. Okay, 2 delta F. So delta F, if you draw the spectrum, so this one will be, for the first one, let me this down. This down. Okay, for the first one, the spectrum will be like this, where this is your FC, is FC plus FM, FC plus 2 FM, until FC plus N FM. This FC minus FM, FC minus 2 FM, until FC minus N FM. This is for, then you have your, what is the value here? You read from your Bessel table. So this is the spectrum for wideband FM. So the total spectrum from here to here will be 2n FM. This is for the first one. Okay, for the first one, which is this one. For the second one, the narrowband FM. Narrowband FM, this means you will have a FC here. Then you only have 2 sideband, one upper sideband, one lower sideband. This FC plus FM, this FC minus FM. So the total bandwidth is very easy to calculate, which is bandwidth equal to this bandwidth wideband FM, this bandwidth narrowband FM. So the answer is 2 FM, because here to here is FM. Since you only have one pair, so this means total bandwidth required is 2 FM. And for this one, this is also FM. FM, FM, then multiply, you have mini. So you have on this side NFM, on this side also NFM, so that's why you multiply with 2. But if our beta is very large, the third one, okay, our beta is very large, more than 10, then we can use another shortcut to help us to calculate, which is, we know our delta F. Our delta F, let's say this FC, the question let us the answer what called the question or the information provided to us, letting us know this is delta F. And then this is delta F. So that means whatever our information, it will sit within this bandwidth. So that means the total bandwidth, for this case, the total bandwidth equal to 2 multiply of delta F. So this is what I call frequency deviation information. Okay, frequency deviation information. So you can see here, provided here, delta F, 75 kilohertz. That means here to here, 75 kilohertz. Here to here, 75 kilohertz. So what is the bandwidth for this actual radio base station? The actual bandwidth occupied for information is 150 kilohertz. Then 25 kilohertz here for upper gap band, 25 kilohertz here for lower gap band. For total one channel, that means information plus gap band, total is 200 kilohertz. So this is the basic information we require for to understand one channel for our radio. So written here is a information signal range. That means this is typical FM signal, meaning it's not single tone. That means it's not one single frequency. This, if we draw the spectrum, that means it might be, the signal might be, that means you have a shape. Here is 50 hertz. The highest end will be 15 kilohertz. So this is the meaning of our information signal range. That means it's not one single frequency. It's not one sine wave or one cosine wave. It's a group of what we call energy at different frequency. This frequency domain, if time domain, we look at human voice, it will be like this, right? It's like music or when we are talking. So we didn't see a very clear sine wave because it's a combination of different frequency. So this is our information signal, very low frequency in terms of hertz to kilohertz. Then the maximum frequency deviation. Maximum frequency deviation, that means for our communication FM radio channel, on this side, the maximum that we can fit our information is 75 kilohertz. Okay, this is upper side, and then this is lower side. So this is the standard design. Standard design, unless in the question it gives you a new design, then you need to look at what the question gives you. So this is plus minus 75 kilohertz. Plus means this side. Plus 75 kilohertz. Minus, that means here. That means this is minus 75 kilohertz on the right hand side. Okay. The range of modulation index. That means the modulation index that we can use in this channel. That means because our lowest frequency is this one for our information signal. Lowest FM is this. So this is FM minimum equal to 50 hertz. FM maximum equal to 15 kilohertz. 15 kilohertz. This is the information provided. Okay, 50 kilohertz, 15 kilohertz. So if you want to calculate our beta, so remember our beta formula, delta omega over omega m. This is in omega, but if a given frequency, it will be delta F over Fm. So two formula. So in this case, we are all our information is given in frequency, not angular frequency, not omega. So we use this formula. So this formula, delta F from the standard design is 75 kilohertz. And then our FM minimum, the most minimum will be 5. The maximum will be 1,500. Okay, 1,500. So that means this is helping us to understand for our FM communication channel, the beta is not constant. The beta will change depending on our actual information that we want to transmit. Okay, that is our FM understanding on how we divide the channel for our FM radio broadcasting system. Any question on this one? Any questions? If no questions, then the last part is on FM stereo. FM stereo, what do you mean by FM stereo? That means you can left track and also right track. So it's like you have a stereo speaker. The inverse is mono audio, and then stereo audio. Stereo audio, that means you can differentiate. You have two tracks within one music file or one what they call transmission. So you have left and also right channel. But mono, only one channel only. That means your voice, your music, only one channel only. So FM super heterodyne receiver shown is monophonic. So that means this receiver, the name for this type of structure, how we build this, is called super heterodyne FM receiver. So heterodyne is referring to how we process the signal there. So we are not going to go in depth there. But the question, the statement just now is saying that if you use this as your FM receiver, you use this structure, the audio signal that you have is mono audio, mono channel, monophonic. That means you won't be able to differentiate left ear and right ear. Stereophonic FM was proposed to make system more natural. So that means the sound will sound more natural. Music and sound can be affected by space, instrument, etc. Stereo allow reproduction of sound with unique directivity and spatial dimension. So that means when you have stereo, you listen to that the music, it can be from your left ear move to right ear, because that's how the music can. If you have a earphone, then you go YouTube, you try out stereo music or stereo train movement, and then you use your earphone, then you turn on the video, you listen that the train when the graphic is moving, actually the sound you listen is moving from your one ear to another ear. That means it's turned on from one speaker to another speaker. So you hear stereo sound. The sound from left side produced by left speaker, vice versa. It is important that stereo broadcast should be compatible with mono receiver. So that means if you are your base station, that means your radio transmitter, that means the DJ or the radio station, if they transmit stereo audio, but at our home, we only use mono receiver. That means our receiver, which is a stereo, for example, FM super heterodyne receiver, is a monophonic. It process monotone, or we call mono channel audio. So our stereo broadcast must be able to backward compatible with this mono receiver, because there's many people still using mono receiver at remote area. So existing mono should be able to retain the monophonic quality. It will receive left plus right. That means stereo, that means you have left channel plus right channel. Mono, there's no left and right. There's only one. Bandwidth equal to left and right equal to 1200 kilohertz, and the frequency deviation is 75 kilohertz. So basically, it's telling us why we want FM stereo, because the quality is you can experience directivity and spatial. But if you have a super receiver, then this stereo signal must make sure it can be received by our monophonic super heterodyne receiver. So you have to make sure our stereo broadcast that we broadcast, it fulfill this requirement. The total bandwidth, left and right, plus together must be 200 kilohertz. Cannot say left channel 200 kilohertz, right channel 200 kilohertz. Then total you need 400 kilohertz, which our super heterodyne receiver just now, that means our receiver here just now, you won't able to cope, because you only allocate 200 kilohertz. So you have to make sure your stereo only fit within 200 kilohertz, and the deviation is 75 kilohertz. 75 kilohertz because that is our design. 75 kilohertz. Okay, then how to design the radio. That means now you have left channel and also right channel. For this one, is not, you're not going to be assessed. This is the last few slides for your information. So we are not going in depth on the circuit. Just browse through. So to let you know, this is a FM stereo transmitter. This means when you transmit, This is our information signal. That's mean from here, example just now, is from 50 hertz to 15 kilohertz. That's mean the signal that we transmit. Usually music, human audio, or human voice, DJ voice, everything fit inside this one. 50 to 15 kilohertz. Okay, so you can see information signal, both of them, our left channel audio, right channel audio. So then this is your stereo processing. Then at the end, you have go through your FM modulation, then you transmit the signal. So you have your, you can see this is pilot signal, then you have left, then you have right. Okay, but we are not go. You do not need to go into in depth in this mathematics and also circuit. You just understand FM stereo. This means you have two channels. Then this is the receiver. So receiver for our normal receiver for mono, it will be this. But now because we have stereo, you need to add what we call a component, additional component to your FM radio, so that it can receive properly. Then you at the output you have two, left and also right stereo. Okay. And also noise is not included in the assessment, and again is as a information for you. So we are not going to go through this because there's a lot of mathematics. Okay, I think that's the end for this chapter. So noise is not within, for stereo noise is not within your assessment scope. The slides provided here just for information, but then there's a lot of mathematics we do not need to go to indeed. So that means your receiver must be able to handle noise. Then how to handle? That means you must be able to just, extract out the noise and then get rid of the noise. Basically, that is what being talked about here. How to get rid of the noise. Okay, that is chapter 3. So chapter 3, if you go back the overview again, as we say, generation and generation of wideband FM is not included. That means if you want to do your study, it will be from page 1 until here. This means starting from 3.9 is not included. Starting from 3.9 is not included in the scope for your test 2, but it is included in your final exam. Okay, so you study from 3.1 until 3.8. Okay, so that should be okay because it's not that difficult. You need to understand, as I say, the key importance page. Key important page is this few mathematics, the narrow band, and then for the wide band. You must know how to use Bessel table. You must know the equations, how to calculate. So all this you need to make sure you understand. Then there will be definitely some theory question. Okay, that is chapter 3 for us. Any question before we go into chapter 4? No question, then chapter 4 notes is already in e-learning. You can go and download. Chapter 4 is talking about the last type of analog modulation before we go into digital modulation. So analog modulation, we learned about AM already, amplitude modulation. We learned about phase modulation. Phase modulation, we have FM. Then we have PM. But PM, we are not going to go in depth. Now here, the third one is pulse modulation. Pulse modulation, this also PM, but then this is phase modulation. Phase modulation, we didn't go in depth in this subject. For SEU, we didn't go in depth. So we focus on FM, focus on AM. Then this one is what we call pulse modulation. Pulse modulation. Okay, so this is chapter 4. So on your screen now, you can see this is a general block diagram for modern communication system. It consists of a lot of block diagram. Let's quickly go through. What you can see, this is the starting for your communication channel. This is your information. And then here, this is your information sync. That means your receiver. Wherever you want to send to. For example, this is microphone. This microphone, you pick up voice. That means your phone, you're talking to someone else here. So this is A, this is B. A is talking to B. Okay, you're talking over your phone. This is your phone. So that means this is your microphone. You're talking, your microphone is picking up your voice, then send through the communication channel, through modulation, coding, everything. Then you go through where? Go through channel. Channel, in this case, if you use phone, this will be our telecommunication network. That means our 4G network, 5G network, 2G network. So this is our communication channel. Then go into the what you call receiver system. Then at the end, this is your friend B listening to the our voice through the speaker. Okay, so the speaker will be our information sync. Information source will be our information picked up by our microphone. So this then you'll go through a different process. If you are a communication system student, then you need to understand all the process what happened here. So you can see we have process of formatting. You need to change your electrical pulses. You need to change your non-electrical pulses into electrical pulses. That means audio into electrical signal. Then this will be your message. This will be digital. Then you go to your encoding, source encoding, encryption for security. So source encoding usually is to reduce what you call the number of bits in your system, so you can save bandwidth. You don't want to waste bandwidth. Encryption is for security. Okay, you want to increase security to your message, so other people cannot, unintended recipient cannot decode your message. Then you have channel encoding. Channel encoding, that means you add more bit to the signal for what you call redundancy. You add any more redundancy, so that if there's any noise happening in the channel, you're still able to retrieve your signal. So that is channel encoding. Multiplexing, that means we want to do many things at the same time. Multiplex. That means you want to send multi-stream of data at the same time. Then you can see now start with modulation. So you have two stages of modulation. One is pulse modulation, what you're going to learn in this chapter. Then you go to band pass modulate. This is another level of modulation. We're not going into in depth. Then frequency spread. This is how you use the what type of technology you use. So this is 2G or 4G or 5G. So they'll use different what they call technique here. Multiple access, that means you want to access the base station. Then you transmit. Okay, this is the transmitter. Then you go to the air. Go to the wireless, what I call radio spectrum. Then lastly, this will be your receiver. Then you reverse whatever process here. If you multiple access, you will have so multiple access here. You frequency spread, you spread, you will despread. You modulate, you will demodulate. Okay. Then at the end, you reverse the process until you get back the information again. So what we learn in this chapter is only one step only, which is modulation. Okay, in our this whole course, we learn about modulation only mainly. So there's many other course talking on different component here. So let's focus on pulse modulation here. Okay, pulse modulation. Pulse modulation is for digital, when our information is in digital. So in the early 90s, telecommunication network is changing toward digital world. That's mean from analog to digital. With the rapid advancement in the field of VLSI, very large-scale integrated circuit, very large-scale IC. So that means basically VLSI is IC industry, semiconductor industry. And then we have a lot of IC chip with a lot of microprocessor able to help us to digitize a lot of information. So several telecommunication components such as transmission line and switching has been using digital signal in their operation. Basically, this statement is saying that this is a digital system. Okay, before this, everything is analog. But now, because of the availability of IC and also microprocessor, then we can send our information, which is usually in analog format. We want to change into digital format for processing, then send to the air. Therefore, information signal must be changed to digital format so that it can be transmitted through this network. This network is a digital network, so you can see you only understand 1 and 0. Binary 1, this communication channel here to here, and here to here, only understand digital 1 and 0, yes or no, logic 1 and logic 0. But our information here and the information that we receive, this is analog. Because human being doesn't understand analog, doesn't understand digital signal, right? We need analog. So we need to change to color, voice, or any other analog format. So this is analog format. We need to change into digital format. Here, from digital format at the receiver, digital format need to change back into analog format. So several techniques requiring full coding of the original source used. So how to change analog to digital? How to change analog signal to digital? This is one big area of study. So example provided here, several techniques to how to change digital signal into how to change analog signal into digital. They call coding. Okay, so coding we have here is listed 4 F5 pulse code modulation PCM. Then we have differential PCM, adaptive differential PCM, delta modulation, and then adaptive delta modulation. So these 3 here is a variation of PCM, pulse coded modulation or pulse code modulation, and these 2 is the family of delta modulation. So we are not going to go through all, we are focusing on a few of them. So let's go through first on digital modulation. The advantage is immunity to noise. Okay, the immunity to noise, we know that for analog, a continuous, let's say take AM, analog signal, we have, let's say this signal is like this. So every value, every dots here means something. Okay, they have different meanings. Every dots on the signal, it means something. Okay, but on digital, there's only 2 levels. Digital only have 2 levels. So this is digital signal. Digital signal only have 2 levels, which is digital 1 and digital 0. This in terms of voltage, this is maximum 5 volt, this minimum negative 5 volt. So let's say because of the noise in the communication channel, then part of the signal is affected. So your signal instead of 5 volt, it become, instead of 5 volt, it become like this. Because of the noise, it become, let's say, negative 4.5 volt. Let's say because of the noise in the environment driver, then your signal by right is 5 volt, but then now it become 4.5 volt. Still okay in digital system, because 4.5 volt, you are still above this line. Whatever above here, you consider as logic 1. So no problem. You can stand to noise for digital system. So immunity to noise. Easy storage and processing, because you only process 2 things, 1 and 0. Instead of this one, you need, let's say, the value here. The value here is 0. Let the value here is 0, 0.1, 0.2, 0.3, 0.4, 0.55, 0.57. So you can see all these have different value. This become the storage. You need more space to store. For this one, easy. You only store 2 bits. Okay, 2 level only. So regeneration, easy to regenerate. You want to generate again, very easy to generate. You want to generate this one, is very difficult because you need a lot of details. Easy to measure, of course, easy to measure. That means whatever above is 1, whatever below this line is 0. This one is not. This one, every single value have a meaning. Very difficult to measure. Enable encryption. Encryption, that means you add in security to your encryption or security to your data. So very easy to do with digital signal. You just scramble them using a scheme. You change, for example, you have one, your data by right. Let's say your data, let's say is 1011 011. Let's say this is a data that you send is a binary, but you can do some encryption technology or scheme. Then you scramble up. You have a way to convert this. You scramble that up, become 0, 1, 1, 0, 1, 1, 1. So you can see when people intercept your message, they won't be able to decode correctly because they do not know what's your encryption key. So here, if we compare, this is very simple. The encryption key, this means we bring this one to the end. So you have 8 bits, 7 bits here. You have 7 bits. The first bit you bring to the end. So that means if you receive this signal, what we do is we move this one to the front. That is your key. If you already know, the sender gives you the key saying that this bit you move to the front, then you get your data. So that is encryption. But it's very difficult to do with this analog. Data from several sources can be multiplexed and transmitted using the same digital communication. Multiplex, that means you have, for example, your this is your transmitter, this is your TX. If you do not analog, only one people can use at the same time. Let's say this is your transmit antenna. Okay, only one analog user can use at the same time. But now, if you use digital, we can enable multiplexing. Multiplexing, that means this is user 1, this is user 2, user 3. Then you will send their signal to one channel. They will send their signal, then they will take Q. Because it's digital bit, we can queue. So this 1, 0, 1, 1, whatever. They can take turn to put in data to the channel. So that's what we call multiplexing. So you can transmit. You do not need to queue like traditional. Traditional, that means you need to queue like this. So after this user finish, after user A finish, then B only can use. But now we can scramble up everything. You can transmit at the same time. Error correction detection. So that means you can put in error correction feature in your binary data as well. Very easy to do. Then you can many ways for us to do error correction. Disadvantage of digital modulation, you need bigger bandwidth, okay, because you need multiple bits to represent one information. Analog signal need to be changed to digital first because in a human world, as a human being, not talking to computer, digital is computer world. Human world is analog world. So that means whatever we want to transmit, we need to change into digital first. When digital system transmit receiving at the receiver, we as a human being, the computer need to convert this back into analog so that we human can understand. So there's another additional process happen there. So analog to digital, A to D, and then D to A. A to D, that means analog to digital. D to A, digital to analog. So not compatible to analog system. So they cannot mix. Digital system cannot mix with analog. For example, you have an analog transmitter. You cannot send to a digital receiver. It might not be able to receive. Need synchronization. Synchronization means here. You can see this is synchronization. So all these components, all these block, they need to be synchronized. That means you need to have a crystal clock or reference clock. So everyone is clocking at the same time. Their pulse is at the same time. Otherwise, you can see if I send you 1, 0, 1, 0, 1, 1, 0, 1, we draw in pulse. Let's say we send you a pulse like this. So the information, if we did the 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0. So then in pulses, it will be like the red color. So this is the pulse that sent. But if you do not, if let's say you and me is not sync, not sync, that means you read data start from here. You're slower. I already sent already, but then you read the data starting from here. Starting from here, that means you missed this bit already. You miss this bit, the information that you receive will be 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, which is incomplete and also wrong. Because when you change into analog, this will be totally different thing. Okay? It will be totally different thing. For example, 1, 0, take a simpler one. 0, 1, 1 binary. This is 3 in decimal, right? So if you miss one, that's mean you miss the number 1 bit because of we are not sync. You miss this bit, what you receive is 1, 1. 1, 1, then you another at the bit at the error bit at the back here, which is uncertain. It might be 0, might be 1. So that means the information that you receive is not 3 anymore, is another number, which is not right. So you need to synchronize. Everyone need to be clocking at the same time. So everyone need to read at the same time. Okay, so that's the challenges of digital modulation. So easy for storage and processing. This is your microprocessor, digital signal processor, your memory, random access memory, random ROM, then your computer. All this is for easy storage and processing. Then in terms of the bandwidth, you can see for voice, for human voice, is an analog. Then usually the frequency is 4 kilohertz. For digital system, you need 2 times 4 kilohertz. You want to change this. You want to change this analog voice into a digital. If you are changing one symbol 8 bit, then you need to have multiply this formula. Later we'll learn about this formula. Then the total bandwidth you require is 32 kilohertz. So instead of 4 kilohertz only, you need 32 kilohertz minimum. Where this formula come from, we'll learn about this shortly. Okay, so this is digital modulation. So whatever mentioned here is illustrated here. So this is transmitted analog signal, and this is the one received. This is what we transmit. This is what we receive. Because of the noise, you can see, for example, this is our audio, our voice. We are talking to our friend through phone, but there's a noise in the system. So the one you receive is actually the this wave line. It's not the actual signal, and this will have noise when you listen to the speaker. But for digital, you can see even though you have noise, no problem. This is still 1 0 1 0. You're still able to record 1 0 1 0 with no problem. So noise is not the problem here. So transmission method for analog and digital signal. So you can see for analog input, analog output. So this is we need modem, and this is modem. So this is whole 100% analog system. Okay, so this is 100% analog system. Information is analog. Information that received is analog, and then the channel also analog. Channel analog, that means real world channel is analog channel. For digital input, if your input is digital signal, that means logic 1 and logic 0, your output is a digital, then your communication channel also digital. What you need is you need an encoder and also a decoder. Okay, that means the whole thing here is digital system. Okay, 100% digital system. But then can be mixture. So this is 100% analog, this is 100% digital. Then they also can be mixture. For example, the input and output is digital, but the communication channel is analog. So you need modem. If your input is analog, output need to be analog. For example, this is voice at the microphone on the transmitter side, and this is the speaker at the receiver side where we listen to the phone. Then the communication channel can be digital. Then you need what? You need ADC. ADC is what? Analog to digital converter. Analog to digital converter. Okay, ADC, analog to digital converter. And DAC is digital to analog converter. Digital to analog converter. Then you need 2 components here. You need conversion. Because the communication channel is digital, you need to change everything to digital. So you need to analog to digital, analog change to digital. Then digital channel only understand code, so you need to have encoder. Then the receiver is a human. We do not understand digital signal. So we need analog output. So you need to reverse whatever done here. So you analog to ADC, then you go to encoder at the transmitter side. Receiver, you need to reverse what they call first in, first out. That's mean no, the last process here will become the first process here. So that means you encode here, then I will do decode first. After decode, we do digital to analog conversion. Okay, then you have your analog output. And the last one is the combination of the above. You have analog input, then you have ADC and encoder, then you have modem. Modem is modulation. Modem meaning what happened in modem is modulation. So you do modulation, this one do demodulation. Okay, that's where the word modem come from. Modem is modulation plus demodulation. So they combine the word modem. Okay, MODM. Modulation, demodulation. Modulation, demodulation. Okay, why we need modulation and demodulation here? Because usually our communication channel not one way only. This is my phone, this is my friend's phone. So we are not talking one way only. Usually we need to both way, two-way communication. So when this is transmitting, we'll do modulation here, and this one will do demodulation. So that means the equipment you have must have two function. You can do modulation, and also you can do demodulation. So that's why we have modem. So here, this is the complete one. So that means you have analog channel, then you change into digital, then you do digital modulation. This is analog modulation. Okay, this analog modulation. This is digital modulation. This analog, this digital. Because your here also you need modem, then you reverse the process. Okay, any questions until now? If not, then we go into our first types of pulse modulation. Then the mathematics is not easy, not difficult. You just need to focus and then make sure you understand the concept first before you go to the mathematics. So for pulse modulation, we have 4 types. Okay, for pulse modulation, we have 4 types. Pulse, that means this is pulse. Pulse is like our what you hear on your EEG. So there is a straight line, then suddenly there's a pulse, then you go back to sleep again, then there's a pulse, then go back to sleep, then there's a pulse, go back to sleep, then there's a pulse. So this is what I call pulse. So we are doing modulation using these pulses. So we are changing our analog signal into pulse. So this is pulse. This is our information signal. So how to do? There's 4 techniques. Okay, 4 techniques introduced here. First is pulse amplitude modulation. Okay, pulse amplitude modulation. So pulse you know already. Pulse is this pulse. Okay. Then modulation we know. We are embedding our modulating information or the information that we understand. We want to embed in this. We want to this pulse to help us to carry the information. But where we carry the information, so there's 4 techniques here. One is we embed it in amplitude. Second, we embed it in the width of the pulse. The third one, we embed in the position of the pulse in the time what we call axis, and then we change it into a code. So there's 4 techniques where our modulating information or the information that we're going to send, it can sit in the pulse in the 4 way. For our sine wave, that means this is talking about analog modulation. We have A cos 2 pi ft plus v. For analog, information can sit in the amplitude. It can sit in the frequency. You also can sit in the phase. So we have AM, FM, and also phase modulation, PM. This is for analog. For digital, is pulse modulation. So you can see in the amplitude, same as this concept. That means the amplitude will carry our information. The width, that means you can see now. Later I will show you the example. Then position, and lastly is the code. So what you see, the parameter relevant, the important parameter for pulse amplitude modulation, PAM, you have your voltage of your PAM and then voltage of your modulating signal. VM is your modulating signal. VPAM is your modulated pulse amplitude modulated signal voltage. So this is after modulation. The voltage will depend on the information signal voltage. Pulse width, that means the time, tau. This is tau. Tau is what? Tau is the, here, your pulse, where the pulse is high. Okay, so this is tau. It's the time period for your pulse where your pulse go high. So that pulse, how long this time will depend on your modulating signal. So this is called pulse width modulation, PWM. PPM, position. That means this is one cycle. This is one cycle, right? This is one cycle. Here, the pulse is always starting at the beginning. Every pulse will start at the beginning of the cycle. But this can change. Instead of sitting here, you can actually sit here, for example. You can sit here. Sit in the middle of the cycle, or you can also sit at the back of the cycle. You can sit here at the end of the cycle. So that means the position can switch. Your period is still the same. No, your tau is still the same, but you can shift around. This shifting of the where it should sit, this is another way for us to do modulation. We call pulse position. So that means delay. So this is the delay. Instead of starting at the beginning, you delay it to by tau t. Tau is time, d is the delay. So you delay. How much you delay? This delay depends on your VM, depends on your modulating signal. Okay, so you can change amplitude. So that means instead of this high, it become low, medium. The height will depend on the VM. Or you change this, become larger. This one become larger or smaller. Then it depends on your VM. That is changing tau. Or you delay the pulse. That is pulse position modulation, PPM. And lastly is you use code. Okay, you use the code in your pulse. So this is PCM. So we'll look in one by one. So what you see here is the top three: PAM, PWM, and PPM. So you can see this is our information signal. Information signal. Now we want to use starting with this one first, easiest, pulse amplitude modulation. So you can focus on the screen now. So you can see pulse amplitude modulation. That means this is the amplitude of the modulating signal, the information that we want to send. So now you can see your pulse amplitude. This amplitude shape, we can see the shape of the modulating signal, right? So usually where you take the value, you take in the middle, so that you either can take in the beginning or you take in the middle. Okay, so you start from here, draw to here, draw to here, or you take the middle. Depends on the scheme that you have. So let's say you take the middle here. This is the middle point, middle point, middle point, middle point, middle point. If you join all these middle point, then you see the shape of your information signal. So this is pulse amplitude modulation. Pulse position, pulse width, PWM. Pulse width, you can see the width here. So this is tau. Okay, the tau is different. The tau is different for each pulse. This is one cycle. This is second cycle, the third cycle. The tau for each cycle may be different. Depending on what? Depending on your information signal. So that means the higher the voltage, the larger your tau. The smaller, the more negative your voltage is, the smaller your pulse. So at the destination, when we receive this one, we read what we read. We read the pulse width. We read the pulse width. Then from the pulse width, we can get back our information signal. And then the last one is PPM, pulse position. So you can see, instead of starting at fixed location, you can see for this one, it's always start at the beginning. For this one, pulse amplitude modulation, it always start at the middle. Always same position, always in the middle. So different system, they have different setting. But for this case, because your amplitude is fixed, you can see amplitude fixed. Tau also fixed. This, the pulse width also fixed. So amplitude fixed, pulse width fixed, but then the position is changing. That's mean within this cycle, you can see this one sit here. This one sit at the back. This one sit at the beginning. So this is what we call pulse delay, TD. To be more obvious, let's say this one. This delay of the tau. Tau is time. Okay, this is a delay time. Okay, so at the receiver, if you receive this PPM signal, you, as a receiver, you just read what is your delay here. What is your delay here in order for you to extract information. Then, especially for this one, it's very important for you to do synchronization properly, because time is very important. This one also very important. So if you not synchronize, instead of reading starting from here, because you are not synchronized to the transmitter, your clock run a little bit, you start to read from here. You start to read this signal starting from here. Then one cycle will be from here to here already. So that means you read the wrong information. The cycle is fixed from here to here. The duration for one cycle is fixed. Then the next cycle will be here. Then you can see you read another wrong information again. Cycle is here. Then there might be error because you have two signals here. So this is the importance of digital synchronization in digital system. So this is pulse modulation. Typical question is asking you to explain. The easiest way to explain is to draw. You draw, then write the names, then write the parameter, then explain from there using your sentences. But diagram will be the best word, best picture to paint your meaning, to show that whether you understand or not. Okay, now we are going to learn step by step how to do this. This is just theory. Now we're going to go into the mathematic part. So please focus on the screen. If you want to change analog signal into digital, you need to go through a few processes. The first step is sampling. Sampling, that means you want to take sample. For example, what you see here, this is two example of analog signal. I'll redraw again so you can understand better. So we have two signals. The first one is a straight line. This is time. This is voltage Vm T. So the signal itself is actually a straight line. Okay, a straight line. Imagine there's no slope. Now you want to take sample. How many samples should take for us to represent this signal? So very easy. The simplest one, you take 2 nodes only. You take 2 points. If I know these 2 points, that means if your receiver in your communication system, you know these 2 points, then you know it's a straight line. Then you can connect them, right? Then you get back your information. But then you want to improve to be more accurate, then you can add more reading. You can add more what you call data point. You can add more. You also can, if you have a higher sampling rate, that means you take more sample. You take more sample. The more sample you take, the more accurate you have. But then you need resources, because every time you take one sample, That means you use resources. That means time and also bandwidth. So this is showing example for analog signal, which is constant. Okay, constant. So sampling that you take 1 point here, 1 point here also can. You take 3 point also can. But based on this one, the sampling is okay. That means you want to change analog to digital. So we call analog to digital is sampling. So sampling, that means analog to digital conversion, ADC, analog to digital conversion. So that's what called sampling. So you take this, then your digital system will take only this periodical point. Okay, it doesn't see the straight line anymore because we won't be able to present everything. We want to take sample. But then for information, seldom straight line. Information, for example, sine wave will be like this. Then it's very important how you take the sample. For example, if I have a sine wave system, let's say I do not draw the axis. Let's say I have a sine wave. Okay, I have a sine wave. If I take sample, not enough sample, I take 1 point here, and I'll take 1 point here, I take 1 point here, I take 1 point here. So that means the sample you have, whatever you have, is only 4 points. So at the receiver, you read this 4 point, you draw, you'll be one straight line. So what's the problem here? The problem here, that means you do not sample enough. You do not take enough of sample to represent this analog. So what you do is, let's say we increase the sampling. Okay, we increase the sampling faster, we take more sample. Okay, now this is better, but then still not enough. Why? Because to computer, what they see is this one, this one, this one, this one, this one, this one, this one. What the computer sees is this, and then when they try to connect, this is the signal that they see. That means this is a signal that computer see, which is not true, right? You lost a lot of information already. So what you do, you increase the sampling again. So you increase the sampling, you sample here, because sampling usually is a periodical. Then you have better. So now you have additional information. The sample that you take is more now. The sample you take, you have more sample now. Then when you draw, then you can draw a better shape. Then the more sample you take, the closer it is to the real or the actual analog signal. So that means this is talking about proper sampling. Proper sampling, you must take. There's a rules for you to take. For example, for this particular case, the sampling rate, the sampling frequency is 11 times of FM. So FM, let's say FM is 10. Let's say for this, frequency FM is equal to 10. 10 is like that. It's 10 hertz. The number of sample you take, you must be 11 times 10. So 110 hertz. Meaning here is every what they call. That means this is moving very slow. 10 hertz, very slow. You need to move very fast. That means the sample that you take, you need to take very fast. So this 11 times. So any question on this one? Or you want me to elaborate further? So sampling is taking sample or changing analog to digital. The keyword is you need to do proper sampling. When analog signal can be exactly reconstructed using this sample. So what do we mean by proper sampling? Proper sampling is when the receiver receives the samples, it must be able to reconstruct the analog signal using the sample that you provided, as I mentioned just now. So the sample here, the receiver must be able to draw back this original signal. If you do improper sampling, they won't be able to draw. The sample contains all the information needed to recreate the original waveform. So this analog is the solid line, and the output is the sample. That means the digital sample. So digital sample, the process is so it's a few ways One way is written as ADC, analog to digital converter. Sometimes written as A/D. Sometimes written as A to D. So it's basically meaning the same thing, just different way of representation. Okay, so now this is talking improper sampling. Improper sampling. You can see the samples, this example here. So if you take this sample, you can see this sample is not that good according to this one, because this sampling is very high sampling rate. So you take a very good sample. But then but the higher sampling you have, that means you need more resources. Your computer is working harder. Then you want to reduce the sampling rate from 11 times to 3 times. To 3 times, as you can see, the sample you take is less. When the sample you take is less, that means you might lose the information, but the information not that far away. Okay, for example, when you connect these two, this information is lost. Okay, if I'm the receiver, I will connect these two sample point together. When I connect these two sample point together, you can see this part is lost already. This information will not be extracted back. But then you're still able to get the shape. You're still able to get the shape like this. So you're still able to, then from here to here, as a receiver, I will connect these 2 points. Then this information here will be lost. So you didn't get back the original perfect analog signal. And this is what we call improper sampling. If you set your sampling improperly, you can see Fs equal to Fm. You take one sample only at each cycle, because the sampling speed and the information speed, they are at the same speed. At the same speed, that means you can zoom in, you can see this is your information. The solid line, this is your information. This is one cycle. So you can see within one cycle, you only have one sample. Okay, one cycle, one sample, one cycle, one sample, one cycle, one sample, one cycle, one sample. So at the end, the sample you have is this dot here. So at the receiver, what you plot this, you join this together, you join this sample together. You join this sample together as your analog signal, which is incorrect, because analog signal is this one, not the what you call this low frequency sine wave that you see. So this is because of you didn't do enough of sample. The sample rate is too low. Okay, the sample rate is too low. The sampling frequency is less than the Nyquist. So keyword here, there's a standard minimum required sampling rate. We call Nyquist frequency. So this is a very key important formula. Typically will be assessed in your final exam or test. It said the sampling frequency is less than the Nyquist frequency. Here, the improper sampling, because the sampling frequency, the frequency that you do sample is Fs, is less than Nyquist frequency. Nyquist frequency is 2 FM. Okay, F Nyquist equal to 2 FM. Nyquist is the name of the person, or sometimes we call the Shannon theorem. Okay, sampling theorem, or Nyquist or Shannon theorem. F Shannon or F Nyquist is 2 FM. So your sampling must be larger than 2 FM. So this 3 FM still okay. This one is 1 FM, which is not good. This one very good, 11 FM. Okay, your sampling is 11 FM, so it's very good. So you get back your shape very perfectly. But the problem with this one is you need a lot of you take a lot of sample. That means your data storage, everything will be more. Your resources you will use more. So sometimes we do want to oversample as well. So we want to take the optimum one. So based on this one, the minimum required, this formula is very important. Fs must be larger or equal to 2 FM. Okay, in order for us to reconstruct the analog signal back. So 3 sampling method, how to do sampling. So the key slide just now telling us Fs must be larger or equal than 2 FM. This is what is 2 FM? This is Nyquist or what do you call Shannon sampling theorem or frequency. So this is the key information for the slide just now. Now we move to sampling. There's 3 methods for us to do sampling. Okay, how to do sampling? There is 3 methods. One is what we call ideal sampling. Ideal sampling, that means you see this is our analog signal. We want to take sample. Ideal sampling, that means we should take 1 dot only, which is this value here, 1 dots. But then it's impossible to do in real life, because in real life we do not have arrow. In real life we have pulse. That pulse, then we have 2 ways. The pulse we call natural sampling. Natural sampling, that means the pulse we have, and the amplitude will follow the shape of our analog signal. The other way is we use flat top sampling. That means whenever you do sampling, let's say you want to do a new sampling using flat top. For here, that means we'll take this sample here, then we'll draw the top flat. So this is flat top sampling. But if you are doing what you call, let me move this to lower place here. So this is flat top sampling. If you are doing natural sampling, that means if you are doing this one, then the shape you need to follow the analog signal. So this is natural sampling, this is flat top sampling, and this is ideal. Okay, ideal, that's what do you mean by ideal? That means doesn't exist in real world. Okay, in every sampling method, the pulse amplitude is directly proportional to the amplitude of the information signal. So I mean the pulse amplitude proportional to the amplitude of the information signal. Practically, ideal sampling is difficult to generate, so very difficult to get this one. However, by using an ideal and natural sampling, noise error can be eliminated. So if you use this method or this method, you can reduce noise, but then it's very more challenging to do in reality. This is easy to do. Flat top sampling, very easy to do, but the problem is you have a lot of noise and error. If you use flat top method to do sampling, then you have a lot of noise, because you can see this is noise. Okay, and then you lost some information here. There's also noise. So these 3 methods: ideal sampling, natural sampling, and also flat top sampling. So if you are asked this question, that means you need to draw, need to name, and need to explain. That is a theory question. Okay, let's look at, let's study the mathematics of the sampling using ideal sampling method. Okay, ideal sampling easier to study. So how we do ideal sampling? We use a very simple, we use our multiplier. So that means this is multiply. So this is our original information signal, or the signal, analog signal that we want to do sample, want to change to. So remember, ideal sampling, that means is analog to digital conversion, ADC. So this is our analog. Then we need a pulse. So this is our pulse. Remember, this chapter is about pulse modulation. So this is our information. This is our pulse. This pulse will be our carrier. Okay, this pulse will be our carrier to help us to carry this information to the destination later. So this is information signal. This is the pulse that we're going to use as our carrier. And then this is a pulse modulated signal. So very simple, you use multiply only. So this, the pulse is a digital signal. Pulse digital signal, this is ideal. So if you are using non-ideal, that means it will be like this. You have pulse width. So you multiply these two, that means multiply this signal and multiply this signal. What you have is your pulse amplitude will change. Okay, so this is what modulation. This is pulse amplitude modulation. When you do sampling, also you can do modulation as well. So you can see this is amplitude of your pulse will change according to your information signal. Very key important, your sampling must be, that means the speed of this, the pulse, TS. sampling period and your sampling frequency. So Fs equal to, let me write properly, Fs equal to 1 over Ts. So Fs must be larger or equal to 2 Fm. So this is for this pulse here. The requirement for this pulse, you must be, Fm is here. So this is Fm. Okay, Fm, one cycle, let's say one cycle is from here to here is, go down. Let's say from here to here is one cycle, Tm, modulating. So Fm equal to 1 over Tm. So this is modulating frequency. This is sampling frequency. Must be larger, at least 2 times of your Fm, according to Nyquist or Shannon. So this is Fourier series for impulse train. So this is impulse train. So this is one is called impulse. Then you have a train of the impulse, we call impulse train. So this means this signal, the name for this signal is impulse train. How we write the equation? For this one is very easy. It's a sine wave equation. But how to write the equation for this one? Because you want to write the equation for this one, right? So you must know how to write the equation for this one. Usually we can express it in a series of a combination of many sine wave function. So this is the equation, the Fourier series equation for this ST here. So that's mean for this impulse train. So it's 1 over Ts, 1 for the first one, you do not have frequency, 2 cos omega st. Omega st, that means you have here the frequency component. This is 0. This is Fs. This is 2 Fs. This is 3 Fs. But this is sorry, this is time. This is not frequency domain. This is time domain. So that means this is for each. You have omega s, 2 omega s, 3 omega s. So this is it will go to infinity. Okay, omega s equal to 2 pi Ts. This is your sampling period. Then is 2 pi Fs, and then Ts equal to 1 Fs. Then the requirement is Fs must be larger or equal to 2 Fm. This is the Nyquist requirement. So Nyquist saying 2 Fs. Sorry, my pen, no battery for a while. Let me charge. So you can see the Nyquist request that the modulating FM, the sampling Fs must be larger or equal to 2 Fm. And then when you multiply the last orange box at the bottom, you can see MST equal to that's mean the sampled output, the modulated output equal to MT multiply ST. Okay, MT multiply ST. So what you have is you multiply that two signal together, then you have this the last equation, the last line equation that so that is not complex yet. So you want to look into time and frequency domain. So the time and frequency domain, let's focus on time domain first. The first graph is your analog signal. That means your modulating signal. ST is your pulse, your carrier. So then you multiply MT and ST. On time domain, the last graph will be your pulse modulated signal, which is PAM. Okay, which is your pulse amplitude modulated signal. If you look into frequency domain, what's the meaning of this? What's the meaning of this? Usually when we draw frequency domain for sine wave, the frequency domain will be 1 pulse, right? This is F for this frequency here. But in real life, it's not single tone, not single tone, single tone. Single tone, that means one frequency. Real life, a lot of analog signal is not single frequency. It will be a range of frequency. So the way to draw is showing that you have a range from 0. That means for this signal, the frequency is from 0 to omega m. So that means you might have a lot of pulses there, but it's drawn as the triangle shape, showing us our information signal actually have many frequency component. Then for this pulse train, when you draw in frequency domain, then you look at this equation here. So you have 0 frequency. That means there's no frequency component. This fs equal to 0. Then this omega s, 2 omega s, 3 omega s. That means fs, 2 fs, 3 fs. So when you draw, you can see this 0, this omega s, this negative omega s. Then you multiply. This one multiply. That means this one multiply this one equal to this one. So this one multiply this one, the output will be this one equal this one. Equal this one. So that means you have 3. You have 1 pulse here, 1 pulse here, and 1 pulse here. So these 3 pulses multiply this one. So this means this will be copied to here. This will be copied to here. This will be copied to here. So like this. Okay. So this omega s, this negative omega s. Then you have 3 pulses. Okay. So this is not pulses. This is axis, showing you the y-axis. The signal you have actually this one, and this one. So this one multiply this one, then become like this. Okay, showing us this is our signal have a range. Then take notes on how you draw this frequency value. Okay, so frequency is copied from here. Okay, so this is digital analog to digital conversion, and at the same time it's also pulse amplitude modulation. Okay, so basically pulse amplitude modulation is sampling, but it's also a type of modulation. Okay, then we have draw in the circuit format. So this is you can see all we are analyzing now in frequency domain. So frequency domain for your modeling in MT, your pulse signal, that means this is your carrier. You have 1, you have 2, and 3 here. No, this is a modulated signal. This info, this PAM. Okay, pulse amplitude modulated. So that means this one. Then you submit to your low pass filter. Low pass filter, that means this is a characteristic or the function for your low pass filter. That means whatever when your omega is below or equal to omega n, then h omega equal to 1. If your omega larger than omega n, h omega equal to 0. H omega is this multiplier. Okay, multiplier. So if you within this one, you have multiply 1. So multiply 1, if this one multiply this one, so that means you can this shape is start at 0. Start at 0, then you will filter out this one. So you can see the shape, this shape here. Then it will be, let me draw the content easier. So you can see here, this is the one will pass through because it's low pass. It's not band pass here. This is not band pass filter because we are talking about half. This is negative, this is positive. We are referring to the positive part. So this is low frequency from 0 to here. This is low frequency. Band pass, you want to draw band pass is like this. Both must be on the positive side. So this is talking on the positive side, this is negative side. So this is low pass filter. Then only low frequency can pass through. This one will be throw away. Okay, same thing here. This will be throw away. This will be throw away. Then you have this one only. Then you go through your amplifier. Amplifier, you can see the amplitude here is 1 over TS. Okay, where this come from? Because that's the behavior. 2 over Ts here, you multiply 1, then it become 1 over Ts. This is after you do mathematics. After you do mathematics, you can see this is 2 here. You have 2, 2, 2. That means you will 2 over Ts. If you open the bracket, you will 2 over Ts, Ts, Ts. It's 2 over Ts. So that's why you have 2 over Ts here. But then after you do modulation, after you this is original pulse. After you do modulation, you can see the 2 is it will be multiplied the MT already. So it become 1 over Ts. Okay, become 1 over Ts. So here, 1 over Ts, how to get rid of the 1 over Ts? So you multiply this amplifier. This amplifier, you amplify by Ts. So the amount of amplification that you do, you amplify the power or the voltage by Ts. So Ts multiply 1 over Ts equal to 1. So your output here is 1. Okay, but then the frequency is the one in the middle only. This one extracted. Okay, so this is transmitter and receiver. This is divided into half. This transmitter, this receiver. So transmitter is very easy, a multiplier. You multiply your information signal with the pulse train. Then this is your modulated signal. Modulated signal sent to the receiver. So the receiver is very easy. 2 components only, 1 low pass filter and 1 amplifier. So low pass filter is you want take middle only, because you can see our information is at the middle. This is our information. Basically, this is just copy. This copy, we do not need these 2. But we need the pulse to help us to carry, so this is replicate. But our information actually in the middle here. So we use a low pass filter. So this low frequency can pass, higher frequency deleted, lower frequency can pass, higher frequency deleted. So this is positive domain, this is negative domain. So this whole shape here is actually the shape for the function for your low pass filter. Then you go through a multiplier with Ts amplitude to match up, to bring up your amplitude back to 1. You can see our original one, this 1. Our original amplitude. Okay, so please, when you study, take notes on all these value. Then make sure you understand the value there. Okay. So to summarize here, sampling process show previously used an ideal pulse. However, it is quite difficult to generate ideal pulse signal practically. The usual pulse signal generator is as below. So this is usually not, we are not using pulse. We are not using ideal pulse. This is a more practical pulse. You must have some pulse width tau. Is pulse width. Okay, pulse width, and this is a pulse period. So when this pulse, what is the equation for this pulse? You can see just now. For ideal pulse, this is the equation. Okay, but for this flat top, because it is flat top or usual pulse, then this is the equation. This is the equation. You can see it's a more complex equation. And then there's a constant Cn here, which is this given by this one, which is sin n pi t. So usually we are not asking you to calculate all these mathematics lah. For mainly you want you to understand later is on the sampling rate, what sampling rate should use, error rate, those things that we want to calculate. So for information signal, you use a normal pulse. A normal pulse, that means after you do sampling, then we can see depends on you use natural sampling or you use flat top sampling. So if you use natural sampling, the data is at the middle here. You can see for this particular case, the value to represent is at the middle. Okay, take the middle value. But if you do flat top and do natural sampling, the amplitude will follow the shape of the amplitude here. The shape of the pulse here will follow the shape of your information signal. But you use flat top, then everything is flat. okay? But then generally you have the shape. If you take the middle, then you have the shape. Okay, you can carry the information as well. Okay, so this is actually sampling. I repeat again, it's a sampling process. Sampling process is actually a analog to digital conversion process. At the same time, coincidentally, this process also we call pulse amplitude modulation. Okay, so that means they are the same thing, but then it's two different concepts. This one is actually doing sampling, because after sampling, sometimes you want to do something else. We want to do other processes. But if you are talking about modulation, this one can send to the air already, send to the channel already if you are doing pulse amplitude modulation. Okay, so this is on sampling. Mathematical analysis, same things. The changes here is just to change the equation for your carrier, which is for your pulse. So same thing here, multiplier. You multiply, then this is your ST. So you after you sample, that means MT multiply ST. So that means here, MST equal to MT multiply ST. So this one multiply this one equal to this one. So the equation part is mathematically like this. So you can see MS is this one. That means this is the modulated signal. Pulse amplitude modulated signal when the carrier is a normal pulse, not ideal pulse. So if your tau is very much less than your sampling rate, the first few harmonics, this one can be equivalent. So this one can be simplified to this one. If you take MT, that means we take our model. If we take example that our modulating signal is a cost function, then we can simplify. You can replace this. We simplify. I just want to go to the end, so you can see here. Look at the frequency component. So this is omega m. This is omega s plus omega m, omega s minus omega m, 2 omega s plus omega m, 2 omega s minus omega m. So how we draw in frequency spectrum. So this is talking about sampling, what you call sampling rate. The choice of sampling frequency or sampling rate must follow the sampling theorem to overcome the problem of aliasing, loss of information. So the problem mentioned here is aliasing, or we call another problem is loss of information. So if you have sampling, not what I call the sampling frequency is not correct, because you can see Fs is less than 2 FM. That means less than Nyquist. So that means your information will be overlap. When overlap, you can see this is aliasing. This is what happened aliasing here. You have overlap here. So overlap here is not good. This frequency spectrum here, not good. That means you have lost information here. So this is not good. So you have to make sure it's larger than 2 FM. So that means this is one set of frequency, one set of frequency, one set of frequency. Then they have some gap between them. So there's not loss of information. So this set of information is not lost. This you can see omega s plus omega m plus negative omega m is this one. Fs, this plus omega m, negative omega m. 2Fs is this one, this set and this set. Okay, so this one and this one. So it's for the second set. Then the equation go on. The equation go on, then this is the second set, third set. So this first one is for this one, this one. Okay, so Shannon theorem or Nyquist theorem state that Fs must be larger or equal to 2 FM. The actual, if you calculate Nyquist frequency, is 2 FM. A bandwidth signal, a band limited signal. That means if your bandwidth is limited, you have a maximum frequency Fx. That means our signal is not single tone. It will be from F min to F max. For example, our voice just now from 10 Hertz to 15 kilohertz. So this F min, this F max. Can regenerate from the sampled signal if it is sampled at the rate of at least 2 FM. That means the keyword here, just to summarize, you must have your sampling rate must be larger or equal to 2 FM. So this is PAM. Next week, when we meet in class, we'll be talking about PCM. But I would like to do, basically that is a content on the cover today. We have another 2 hours we need to replace. If you do what they call replacement class on Monday night, you're available? Monday night or afternoon, anytime that you're convenient. Okay, then I will send the link to the group. Then we'll go through the information together. So not much. You can see for your scope for your test 2 is up to so up to slide 36 and no up to slide 35. Okay. So this is 464 non-uniform quantitation from this forward, and also line coding is not within your scope for test 2. So we are not very far away. I think next Monday we can finish. Then Tuesday and Wednesday we'll do exercise together. Okay, before your test on Wednesday. So before we go for Monday, please take time to study. So typically the questions for, if the scope is until there, popular question is like this. So you try to uniform quantization. That's mean how to calculate all this value, how to assign all these, that's mean how to calculate all these things. That is typical past year questions. How to draw. So if you go and study first, it will be very easy. So this is typical of questions, quantization error. So you want to learn this in Monday. So the example, quantization, how you do. So definitely for house modulation, there will be 1 questions. Then we will theory. Then because we do until PAM and TCM only for uniform, then typically this question, definitely there will be 1 questions. Similar to this, to calculate all these, either ask you to draw, then ask you to calculate quantization error, all these things. Okay, so today we talk about sampling. Then next week we'll talk about coding. Okay, PCM. And then that's the scope for your test 2. Okay, any more questions for today? If no, then let me take your attendance before you go. Let me get the attendance list.
Doctor.
You need to speak louder.
Doctor?
Yes, you need to speak louder.
Oh, sorry. I want to ask, will you send the recording for this session? Or not?
I can send, but do not rely on this recording only, because the lecture only give you a overview. I will send the link, but as I say, do not rely on the lecture only. You need to do your own self-study and also exercises of the past year question and everything. Then if you have a question, then ask me in the class. Let me share the attendance. Let's stop sharing. Attendance. Okay, I'll call your name, please. Turn on your mic. Nabila,
Yes, doctor.
Rehan,
Yes, doctor.
Binto,